the um, the minutes and the video of the presentation are all being posted to the IRP website. If you have any questions about where that's at, I can provide that location. The information for the first IGRAC meeting have been posted. So if you missed the first IGRAC meeting and want to watch the first meeting, it's out on the webpage. So we'll go ahead and first get started with introductions. So I'm Brian Robertson, manager of supply resource planning with Intermountain. I'll go down the list of people, and if you can, just hop in, provide your name, your position, and the company you're representing. Kathleen.
Oh, good morning. I'm Kathleen Campbell. I'm a senior engineer with engineering services for Intermountain Gas.
Thank you. Jenny.
Hi, I am Jenny DeBoer, resource planning economist under Brian's team for Intermountain.
Thank you. Ryan.
I'm Ryan. I am a resource planning economist with Intermountain Gas.
Thank you. Jason.
Morning, Jason Talford with the Idaho PUC.
Thank you. Matthew.
Matthew Hunter, President and CEO of the Pocatello Chamber of Commerce.
Thank you. Mike.
Hey, good morning, everyone. Mike Parvinen with Intermountain's regulatory team.
Thank you. Rebecca.
Rebecca Wildman, Business Plus.
Thank you. Mark.
Good morning, Mark Sellers-Vaughn, Upstream Resources Manager for Intermountain.
Thank you. Sanjay.
Morning, everyone. I'm Sungjae Lee. I'm engineer in PUC.
Thank you. Zach.
Services with IGC.
Thanks, Zach. Bailey.
Good morning, I'm Bailey Steves. I'm an economist on the resource planning team with Intermountain.
Thank you. Vicky. Vicky, if you're speaking, you're on mute. Okay, maybe she had to step away, but Vicky is with the PUC, I believe. Kathy.
Good morning, I'm Kathy Wold, Manager of Energy Efficiency.
Thanks, Kathy. And Eric.
Yeah, good morning. Eric Wood, Gas Supply Manager at Intermountain.
Perfect. I'm just scrolling the names again. I don't think anyone joined since we started doing introductions, but if anyone did jump in and I missed them, please introduce yourself. Okay. All right. So yeah, then I'll jump in and give some a slide on how to provide feedback, and then we'll go through the agenda for this meeting. So for feedback, you can reach out to us at irp.comments@intgas.com. If you have feedback that comes in after this meeting, obviously during this meeting, feel free to jump in throughout the presentation. You can either raise your hand or put a question in the chat, or just come off mute and interrupt us and say, hey, I have a question. We're happy to answer any and all questions that you guys have. And if we can't answer it today, we'll try to get back to you as soon as possible. We are asking to get comments and feedback within 10 days, especially if you're hoping to get any changes to methodology or anything like that into this IRP. It's a lot easier to get that done earlier on in the IRP process rather than later on in the IRP process. So any feedback, if you can get it within 10 days, that would be very helpful. And then here's the location of the IRP webpage. If you just copy and paste that into your browser, it'll take you right to our IRP webpage, and you can find the schedule, meeting information for IGRAC 1. And I believe the previous IRP is out there as well if you're interested in reviewing that. So jumping into the agenda, so we did the welcome and introductions. I'll do a quick safety moment after this slide. And then Kathleen and Zachary will be providing a distribution system modeling presentation. And then we'll have an avoided cost methodology presentation, energy efficiency presentation from Kathy, and then supply resources and transportation storage resources from Eric. And then we'll open it up for any final questions at the end. But again, feel free to ask questions throughout the presentation. So just a quick safety moment. I know it's the summer is wrapping up, but it's still pretty hot out. It's been over 100 degrees here the last couple of days. So make sure you wear a hat and sunglasses. You want to protect your head and your eyes. The sun can be really damaging to both of those. Make sure you drink a lot of water. Make sure you drink water before going outside in the heat. Don't wait until afterwards, or else you could dehydrate yourself. Make sure you use appropriate sunscreen. The time of day matters. So the UV rays are strongest between 10 a.m. and 4 p.m. So you'll want to try to avoid those as best as possible. I know that's a little bit difficult. And then if you are outside, make sure you find shade. Try to avoid standing out in the sun for too long. And then make sure you get under the shade and can get some reprieve every once in a while from the sun. I guess I have an additional slide before we get to Kathleen's presentation, but we provided the screen information in the IGRAC 1, so an economic overview, residential and commercial customer growth, design weather, and industrial demand. And then today's presentation, what we'll cover is residential and commercial usage per customer, transportation capacity and storage, natural gas supplies, non-traditional resources, and then energy efficiency, residential and commercial. So all of that will tie into demand and supply and deliverability that will be presented at IGRAC 3. So this is kind of showing how all of these are going to tie together. And just a reminder, we focus on areas of interest with our IRP. So we have 5 areas of interest, and then in all other customers. So you can see there, Canyon County, Central Ada County, north of State Street lateral. Those are all in the Boise area. And then we have Sun Valley lateral, which is more central Idaho, and then Idaho Falls lateral, which is more eastern Idaho. And then all other customers are spread across Idaho. Okay, are there any questions before we jump into distribution system planning? Okay, I'm not seeing any questions, so I'll pass it over to Kathleen.
Yeah, I'm going to take the screen. Good morning. I think I want this screen. Let's see. I'll get set up and then we'll get going. Here we go. So yeah, I'm Kathleen. I'm going to go through the presentation, and I also got Zach with me. He's going to help like answer questions and maybe keep an eye on the screen, Zach. In this setup, I can't see like if hands get raised, but we're kind of informal, so feel free to interrupt, jump in at any time if you got a question, and Zach can help too. But yeah, we're going to talk today about distribution system planning. This is going to set us up for IGRAC 3. So in this one, just high level, we're going to talk through what a deficit is, what tools we use to assess deficits, and then once we identify the deficits, some of our philosophy on alternative analysis, and then how we get to the capital budget process of getting a project planned and then constructed. And then the actual projects will be in IGRAC 3. So this is going to kind of set us up for actually going over the projects, talking the lingo. So it's a good setup. And then the next one's kind of the fun one, I think, because we get to talk about the projects. But yeah, so to get us in the lingo, Intermountain Gas, this is just a brief summary of our system dynamics. We have a range of operating pressures and pipe diameter sizes and materials, as you can see. You can see the miles of our distribution and transmission lines on the fourth bullet. But we operate a diverse range of pipelines, over diverse pressures. And in addition to piping, we also have facilities. So we have over 600 reg stations, and then other equipment such as LNG, gas quality, odorizers, and compressors. And then a couple photos here. First one's a regulator station, second one's an odorizer, and the third is a heater. And then just so this is like a very high level like view of our system, but it kind of explains Intermountain Gas's system. So Intermountain Gas, we get custody off of Williams Northwest Pipeline, which is an interstate pipeline. It's a gas transmission line. And it runs from Utah all the way over to the Pacific Ocean, all the way over to Seattle area. So that's kind of the pipeline that we get gas off. And everywhere the Intermountain Gas takes custody of, there's a gate station. And there's two sides to the gate. There's the Williams side and then the Intermountain side. On the Williams side, they meter the gas. And then in some instances they can regulate, but they basically transfer the custody of the gas over to Intermountain. And then Intermountain, we will regulate and then odorize the gas and then send it down our high pressure pipelines. And the high pressure pipelines in this example is red. And then, along our high pressure pipelines, we'll have regulator stations or we can serve our large volume customers direct. So the little gray boxes are factories. So depending on what their contract demand is and, what equipment they have and what pressures they need, they can either be served off a distribution, which is blue, or the red, which is high pressure. And the regulator stations, they're kind of the start of our distribution system. They typically cut the high pressure down to distribution. And typically that's about 60 pound MAOP. And then the blue pipe, is what serves our core. So that's what runs like to our residential and commercial customers. And then a typical house has a 14 inch water column meter. So all the way to the meter is the distribution. So that's kind of the quick summary of just how the facilities work. And as we start talking, about our systems and where deficits are, where problems are that we need to address, it's good to kind of understand the dynamics. And then I think I mentioned, but the main tool we use to assess our system is a gas modeling software called Synergy Modeling or Synergy Gas. It's distributed by DNV. And with these models, we get to evaluate for growth, deficits, they'll support emergency, if we need to do shut-ins or valve shut-ins or things like that in our system. But they're the main tools the engineers use to understand our system and give guidance on it. And these systems incorporate all of our customer loads and our piping and system configurations. And then their main use and what we mainly use them for is, they're used to predict peak flows and pressures on our systems during that peak weather event. So that cold day when everyone's using gas, which is the most extreme condition on our system, that's really, what we use Synergy gas for. And it's to make sure we can meet all of our deliveries. And then our models, we go through a robust model rebuild process. They're updated every 3 years, and then we maintain them between rebuilds. So if we have like new large volume contracts, or let's say some RNG comes on the system, or a new subdivision, or maybe they punched through a new road and we reinforced a system, looped something, that's all updated, as it happens by our engineers. And then just to help you understand Synergy, it's a visual model, but this is an example of our GIS. So on GIS you can see, and this is kind of what we've been talking about, but on this I can see, I got my cursor over here, but this is a gate, it's a square box, it's hard to see, and then these little red boxes are regulator stations. So I can see a gate, which is where we take custody from Williams, motorize it, and then I can see this high pressure line. So I can see kind of running, you can kind of follow the regs. It's kind of running to the west. And then off of that, these regs cut, and then you can kind of see the distribution pipe. And in this example, we have blue pipe and green pipe, which I think is just the material. So I think green is steel, and then blue is plastic. And it just depends on the vintage on whether distribution pipe is plastic or steel. Typically, plastic came in around the mid 80s for Intermountain gas. So it just depends on the vintage, but this area over here is distribution. It's just steel because it's a little bit older. It's in downtown of this example. But yeah, that's what it looks like. And then Synergy, it's a spatial model, but we'll take the GIS data and it goes in Synergy. So you still have our reg stations, our gates. They look a little bit different. I think gates are circles here, and then the regs, you can kind of see in gray. And then the piping's the same. But it's all unique, in the customer served and the pipeline characteristics. And then I'll just touch a little more on the model building process. So I mentioned they're rebuilt every 3 years and then maintained. And then when we rebuild them, we bring in the new GIS data to build the spatial data. Even though we maintain, as you go, you never know if you miss something. So we always refresh them, bring in all new data. And then we also export 5 years of our CC&V billing data to a module in Synergy called CMM. It stands for Customer Management Module. And that allows us to create an updated demands file. And we update that billing data every 5 years because, maybe, we want up-to-date billing data. Maybe they put a new piece of equipment in their house, maybe added a gas stove or gas dryer, or maybe they've had a trend change, like maybe their kid went off to college or something. So we want up-to-date data on everybody, or, they could have sold the house too and have a new, whole new, usage curve potentially. But we validate and calibrate each model to a recent low pressure event. So once we kind of build the models, bring the data in, we check them. And that's kind of calibrating. And a best practice for calibrating is we want to be built within about 10% of the actual data. And some of the data we'll use is, we call them ERXs, but that's kind of a pressure chart, or it's a more modern pressure reader that is electronic. I think it's an electronic pressure chart. And we get that data through radio. But SCADA, Metratech, or the large volume usage. So all of our data points we can look at and then see how it's performing to that low weather event. It just gives us confidence in the models, in the new models, that they're performing as we expect. And then once we get a model that's kind of calibrated, we'll create a design day model. And I'll go over that in a sec, but that's basically we increase the heating degree. We set up the model with the heating degree day that we get from gas supply that is the coldest average daily temperature over a 30-year period. And like I said, it's a historical weather trend. And that's what we want to use for that really cold day, that peak day on our system when, the most gas we've seen or could see, I guess, be used. And we want to make sure that we have like reliability and can meet that. And then actually our IGC models we've been working on, they just got rebuilt this year. So we have brand new models for our IRP assessment this year, which is good timing. And yeah, and we're kind of through the calibration process, and we're working through the growth modeling right now. So here's just some slides just to maybe understand a little more, a little better understanding. But for data gathering, this is just to see C&B. This is our customer billing data. It kind of look like if you get a gas bill, but you know, your therms usage per month will be in here in the trend, and this is how we get the 5 years. So this data gets you know, transferred to Synergy and, you know, put into the models. Other data modeling or gathering is, this is our SCADA. So this just shows our pressures and flows on our systems. So we'll have different pressures, transducers, or points we monitor. And we can look at that data to help us calibrate and see what's going on the system. So other data gathering, and I've talked about this, but this is always good to define, but this is our heating degree day. So for Idaho, this kind of shows our heating degree day for all of our districts. And the heating degree day, it's always based off 65 degrees. And 65 degrees is kind of the magic number when everyone turns on their heat. So as we get into fall, we're gonna, you know, be experiencing this in the next couple months. But when it gets to about 65, you get a little chilly, and typically people turn their heat on. So everything's kind of related to 65 because that's when your base load comes on for your heating. And then if you have a heating degree day, you know, you can get an average daily temperature, but it's basically your heating degree day is 65 minus your average daily temperature. And it's always good to talk through one, so I'll just talk through one. But for Boise, their 30-year historical low weather event is minus 10 degrees Fahrenheit. So if we take 65 minus a minus 10, we get a heating degree day of 75. So that is what we build Boise for and kind of assess deficits on, which we'll get into next. I'll pause. And this one always can be. Sometimes we can get some questions. Any questions so far? Okay. Oh, this is just an example of our customer management module. So this brings that CC&B data into Synergy as a demands file. And we typically, just for data storage and things, we don't model to the meter. Something that CMM does is it puts it into the pipe loads. Just with data and processing for the model runs, CMM just helps us load data into pipes. And it's supplied spatially. An example of this would be if you have a subdivision, you know, with a section of pipe, you know, let's say there's 10 houses on it. You know, those 10 houses, instead of having individual meters, we just put the 10 houses into the pipe load. And it works the same, it just makes the model run a little more efficient. And it's a better data management practice. And now I'm going to get into how we go from a calibrated model to a peak heating degree day model. So with our data and with our CMM data, we can get this on our system, but we can know with degree day, and I'll put my mouse over here, we as the degree day gets, and remember this is always from 65, so as we get colder, so basically 0 is no heat load, so as we're getting colder, you know, more usage, MCFH, more use, you know, usage goes up, takes more to keep the space heated with heat transfer. So that's kind of how we do it. So we can always get a, you know, and this happens to be a linear regression or linear relationship between degree day and MCFH. And we can find our, you know, we can do a linear regression and get our slope and our y-intercept, which is heat and base right here. And then we can always know what we calibrate to. So for an example on this one, if we're going to calibrate to a 40 degree day, which would be 65 minus 40, or 65, yeah, minus 40. So we would be 35-degree day. We know that this linear relationship, we can always ramp up, and that'll help us find our peak degree day. So even if we don't have the data, we can extrapolate. And that's kind of what happens on the peak heating degree day, is it helps us extrapolate up to find, how much the usage is. And that's what we build for our, our peak scenario for modeling. And now, so that kind of covers our modeling. So that's kind of the tools we use to like get our deficits and look at our systems. And now I'm going to transition a little bit into, how we identify system deficits and constraints. And then from that, then we'll get into all, alternatives. There's always like potentially multiple ways to fix a problem. So with synergy modeling, we just talked how we build them and then get to our peak heating degree day model, but this just covers how we use, how our engineers use the synergy models all the time. So we spend a lot of time like rebuilding them, calibrating them, so that we have an effective tool to, sorry about that. So we can review our large customer requests, model RNG, if RNG is feasible or if our system can take it. We can size and design our pipe and pipeline components. We can do future planning, model predicted growth, identify the deficits, determine our system reliability, identify weak spots or maybe spots, places where we need reinforcements or pipe looping. We can look at our distribution enhancement options. So it allows you to compare options so you can get, capacity gained, for the different options, and it can help you, determine, your alternative analysis. And then we can also look at cold weather action plans and model curtailments and interruptible customers. So lots of, tools and opportunity for synergy gas. And then I'll just cover what a capacity deficit is. It's defined as a critical system that is at or limiting capacity. Some of these examples include a pipeline bottleneck, a minimum inlet pressure to a reg station or high pressure system, minimum inlet pressure to a compressor, which is called the suction, or a component limiting capacity. So I'll just give a couple examples, but a component, some things like an odorizer or even a regulator station will have a rated capacity. They'll be depending, and sometimes they're typically a function of pressure, but not necessarily. But there'll just be a limit on how much it can peak. So we can always compare our components to what's predicted in synergy and find out if we have a deficit. And then another example of a deficit is, a high pressure system. So let's say I have a 500-pound high pressure system that's feeding a 200-pound high pressure system. If my 500-pound system, where it goes to the 200-pound system, only has 100 pounds, that would be a deficit because it's the flow in the 500-pound system has pressure loss, because the flow is being exceeded. So pressure loss increases and it's compromising the 200-pound high pressure system. So that would be an example of a deficit. So you would need some kind of enhancement on the 500-pound system to, get your 200-pound system back into, where it's supposed to be operating. I'll continue. And then with this, I think I've touched on this, but with our modeling and everything, we make sure we can meet the growth predictions, which is the main part of the IRP is, 5-year growth planning. So we do our comprehensive reviews every 2 years with the IRP, and that ensures we can maintain reliable service to our customers during those peak low temperature events. And then it also times up with our capital budget cycle. During the IRP year, it times up, but then we also do capital budgeting every year. So a lot of this is being looked at every year. Just some of the growth modeling. We do a little more detailed review on the 2-year cycle of the IRP. Anytime we predict a deficit, it's evaluated by engineering, and we will look at alternatives, for reinforcements or enhancements. And then typically we select that and it's placed into the budget, and it's all based on the timing needs. So a lot of things we do with growth modeling is we'll predict the exact, year the deficit happens. And then we have to make sure that we have a project in place or a enhancement or, whatever the betterment is, so we can avoid the deficit. So now I'm just going to go over options. So since we're talking, and this is setting us up for IGRAC 3, we'll talk about, enhancement and reinforcement options to address deficits. So for a pipeline, I've mentioned a couple of these, but we can always do a replacement or a reinforcement. We can do loops or backfeeds. There's potential for pressure increases and or uprates of a pipeline. So we can retest, or depending on the records, complete an uprate to operate at a higher pressure. Like I gave that example of that 500-pound to 200-pound system. Maybe you can, an example would be potentially uprating the 500-pound system to 600 pounds, to not allow it to compromise the 200-pound system it's downstream feeding. You can also do facility upgrades. So if you need to replace a component, like I said, a reg or an odorizer that's at max flow, that's limiting capacity, you can replace those. For distribution, you can always add a regulator station. So regulator stations are kind of a fresh supply of 60-pound gas. So if you have a low pressure area, that can be a solution for distribution. Another option, and this can help high pressure, is you could loop or add a gate station. And then on large laterals, and we have a couple of these, you can add compressor stations to boost end-of-line pressure on the laterals. And then I think I've mentioned this, but all of our systems are unique and will be optimized using different enhancement options. And some of these, it depends on what you have on what's favorable for your enhancement. And this is just an example. It uses a little bit of synergy, but this example, we'll just walk through a scenario, but this is a theoretical low pressure scenario. You can see pressures on the right, but the area we're concerned on is this 10-pound area in red. And you can see here, I'll just put my mouse. So this is our gate. And then we got a couple regs. So we got a little bit of high pressure. And then it looks like, I think the rest is just distribution based on the colors. So if I wanted to serve this red area, what options would I have? It looks like we could loop, maybe loop here. Maybe extend high pressure, bring another reg down here. A couple ideas, but we'll work through them. And I think I mentioned, compressor station wouldn't be feasible for distribution, but just as we're thinking through ideas, you could look through that previous list. Here's some regs. Some pipe could be an option. And I guess this reg's like saying maybe it's maybe the capacity of the reg's limiting. Maybe it's limiting flow, so that could be something you check. But if you're good, then you might be looking at pipe. But option one, so that was just our synergy. So we always have to kind of vet, our enhancements. In this example, this actually turned out to be an airport. So you'd probably be unlikely to run pipe under runways. Probably wouldn't go over well. So you maybe have to look at a different scenario. So that might be the shortest, or might boost the pressure the most, but it might not be feasible. Another option down here, so this looped it, and then it's recolored, so it reran the model. So you can see it got everything above 10 pounds. So that's just an example of how an engineer would work through, identify a deficit, look at options to address the deficit, and then come up kind of with a good alternative. Just on a high level example. So, and with enhancements, so now that we're kind of thinking about, enhancements, but this is always things we consider, is we always look at scope, cost, the capacity increase, the timing, the system benefits. We try to do alternative analysis just to make sure we're getting the best alternative that, not just the first thing we tried that worked, but, vetting them. And then we look at feasibility, like, and some of this, it'll play into each enhancement will have pros and cons, and they'll be kind of weighted out in that alternative selection process. And the engineers kind of work collaboratively with management on this, but there's several factors that you could consider, like environmental, is it in environmentally sensitive areas like wetlands or a stream crossing or a bank? Maybe those would be areas to avoid. It may take more permitting, or is it in tribal land? Things like that would be vetted out. And then it could also include like feasibility, like I think I mentioned, like a compressor, they work well on laterals, but wouldn't work as well, in a downtown area. So just different things you'd play out and consider with alternatives. So I'll keep going. So with that, we kind of have gone over, and I'm going to just briefly cover how they get into our budget. So in general, we have, and I talked through this a little bit, but this is our general enhancement selection guidelines. So we want like the shortest segment of pipe, that addresses the deficit, most cost-effective solution, favorable construction conditions, minimizing environmental concerns and impacts to the community. Maybe something you could consider is, pipe routing or looping is maybe there's opportunity to add customers or even large volumes customers. And then we always look at total construction costs, including restoration. So traffic control, asphalt restoration, things like that. Maybe permitting, like if you got to cross a major highway or a railroad, things like that. You might have a road moratorium or another construction impact, that might also limit your alternatives. And a road moratorium is when a city's recently paved a road, they sometimes won't allow construction on it for so many years. So sometimes we have to navigate that with the cities because they just don't want their new road torn up. And then with this kind of builds in everything we've covered, but basically we take our, this is how we get through our enhancement selection processes. We take all our IRP growth data, that's in Synergy, look at the models, put them into the design day models, and then we consider our engineers, they cover certain districts, so they're very familiar with like what's going on in their district, the new housing development, maybe there's plans for like commercial areas or a new shopping complex or things like that. So they're keyed in on developments and, road projects and things like that, maybe road widening or turning circles. So all that kind of goes into, helping us choose our enhancements, using the model. And then we look at our system limitations and kind of come up with alternatives. And then we take, and all this is kind of iterative. They work collaboratively with, managers and directors, for the reinforcements and, how we select them. But they kind of go through this process where we look at benefits, feasibility, and cost. So they're identified, and then we'll have the alternative kind of laid out, and then we'll typically select one, and then they'll kind of get ranked. Oops. And they'll get ranked based on their priority. So this kind of is neat. So it's like timing of the deficit, or maybe there's a road project, or whatever the priority is for the project. Could be city development or a turning circle or something like that we know there's a deficit, and maybe that's our favorable alternative. And maybe there's a reason, where we schedule it in the budget to make sure it gets complete to avoid the deficit. And then they're placed into the budget with kind of that knowledge. So that's kind of how we build up and work together to put in the budget. And then with this, it's always iterative. And then as information changes, we can make tweaks as needed to the capital budget. Right now, we're kind of in the capital budget cycle. So our first pass of the budget was in June. I believe we just completed the second pass and we're working on the third pass. And then our full capital 5-year budget typically gets approved by the board in late November. And then our budget year starts in January. So So we're working on that, and those projects that are in the budget are what I'm going to cover in the next presentation. And then this is my final slide, but this will kind of wrap up. But I like this slide because I like to show the iterative process. So kind of what we've been talking about is every 5 years, and this hits on the capital 5-year budget too, but we're planning every 5 years. So in 2025, we're looking out to 2030. And then when we do 2027, we'll have some overlap years. And the good news is when we assess every 2 years, maybe we can adjust timing a little bit on a project. Maybe we didn't see as much growth, or we saw more growth, and we need to move the project, back a year or forward a year. So everything kind of gets like re-reviewed, looked at, making sure we are on top of deficits and that we're addressing them. Also with the 5 years, it gives us time to plan and construct a project. Some projects, some larger scale projects take multiple years to complete. So by doing the IRP, if we know we're going to have a deficit in 2029, we can plan, acquire land, order long lead items, etc. So to make sure we can get it complete in 2029. So I like that, and I like to kind of show the planning and then the overlap of the IRPs, and our ability to kind of adjust a little bit, as based on what we're seeing. So like I said, like RNG could come on our system, which would be a new source, or just some of the changing dynamics, even in the natural gas industry. And so this kind of shows that we have a lot of confidence to like adapt to these changing dynamics, and avoid the deficits. And like I said, this will set us up. So now I think we've kind of like understand the methodology, the tools we used, what a deficit is, how we work through alternatives and what we consider to set us up for IGRAC 3. And in IGRAC 3, we'll go over the distribution projects that are in the budget, in the 5-year budget, and give updates, from previous IRPs. But that's all I got. So I'll open it up to questions. I'll stop sharing. Okay, well, I'll hand it back to Brian, but thanks everybody. And
Yeah, thanks, Kathleen. If anyone has questions, go ahead and jump in and ask. If you want to wait till the end, you can do that as well. Okay, so we'll jump into the avoided cost portion. Zach, are you on the call and able to present this section? I think there may be some technical difficulties there, Zach. So I'll just go ahead and jump in and present the section. Let me turn my camera on. Yeah, so so just a little bit of a brief history on the avoided costs. So order number 34538 in Int G 1904 directed the company to review its avoided cost calculations. In early 2020, Intermountain put together an energy efficiency stakeholder committee and joined the avoided cost subcommittee to meet. They met 3 times between February and June, and this is where they came together and came to an understanding on general avoided cost methodology. The avoided cost subcommittee met in March of 2022, and there was a lot of discussion around distribution system costs and how to handle those in the avoided costs. There was discussion on whether to use historical data or use future data, but ultimately there was an agreement on how to handle distribution costs, and so therefore it's just set at 0 for this methodology. And then in order number 35663, the commission approves the company's proposal to streamline avoided cost updates by including them in the IRP filing. So you'll see the avoided cost as an IRP filing from here on out, and discontinue their inclusion in DSM prudency filings, and align program planning and cost effectiveness testing with the most recent IRP and applicable avoided costs. So what is an avoided cost? Essentially, the avoided cost is the dollar amount that you're looking at to replace on the upstream side. So instead of buying a molecule of gas, a decatherm of gas, and sending it to a customer, can you use that money and cost effectively use it towards energy efficiency and reduce a decatherm of gas? So this allows the utility to spot opportunities where energy efficiency is more cost effective than a supply side option. So here's the natural gas supply chain. You have the production, so where the gas comes from. This is generally the built into the commodity cost. So when you go and purchase the gas, and then there's the transmission. So when you transmit the gas to your system, so to the city gate level, and then there's the distribution. So your distribution costs to get that gas to your to the house or to the commercial building. So yeah, here's the commodity costs, the transportation costs, and then the distribution costs. And so to break that down into a formula, here you have your avoided costs, which is in nominal dollars. It's equal to commodity costs plus transportation costs plus variable distribution costs, which again is 0 for this IRP. So what is the commodity costs? It is the price of a molecule of gas, and it depends on the basin, the time of year, and even the day of the week of when it's purchased. The calculation starts with an internal 30-year price forecast for 3 primary basins: Sumas, Rockies, and ACO. And then these prices are weighted based on the company's day gas purchase. And then we use a normal heating degree day of HED 65 to shape the monthly prices. So the transportation costs, it includes the reservation rights to move the gas. And then it's also based on the volume, the amount that you move on that per a given day. For RS, which is the residential, and GS1, which is the commercial customers. And yeah, like I said, the variable cost is dependent on how much you move on that day. And for the IRP, we're just focusing on 1 decatherm. So it'll be one decatherm worth of reservation costs and 1 decatherm worth of variable costs when doing this calculation. So distribution cost calculation. So like I had mentioned, there was some conversation about using historical data, using future data. One thing is energy efficiency can lead to delaying or even avoiding costly pipeline capacity expansions. Large expansions occur irregularly, making it difficult to quantify this type of savings. Currently, we do use a value of 0 for this. As part of this IRP process, we will continue to work with stakeholders. If any stakeholder thinks that distribution costs would be important to include in the avoided costs, we're happy to have that conversation. That's kind of the reason why we include it in this presentation, is we do think it's important to include this calculation. But right now there's just not an agreement to include it. So any feedback on that is appreciated. And then the 2025 IRP updates to the actual values. So again, we've updated the basin price forecast, which is, I think it's further described in Eric's section. So we'll get to the basin forecasts later on in this presentation. Updated HCD shaping to use the 2024 normal weather data. So that's normal weather as of the end of 2024, not saying 2024 is normal weather, just to clarify that. Added new year of day gas purchase data, updated transportation costs with latest PGA tariff, and then updated the inflation rate from 3.15 to 3.99%. And then you could see the previous cost and updated cost for this IRP. So you can see it's actually dropped quite a bit, especially in the earlier years. And then it gets pretty close towards the end of the planning horizon of 2030, 2031 timeframe for the IRP. And the main reason for that is because commodity costs have come down a little bit, especially in the price forecast. Are there any questions? Yeah, Jason?
Great, thank you. Yeah, just a question on, for those updated costs there, how firm are those? Are they likely to change at any point between now and, when the final IRP is filed?
So I don't expect them to change unless anyone wants to see something different in the avoided cost. So what happens is these values get sent to Kathy, and then Kathy updates the energy efficiency modeling, and it provides demand side projected savings from the energy efficiency programs. So likely these will be locked in and won't change. But obviously we're interested in feedback on this process.
Okay, thank you. Yeah, I guess I'm still forming this question, so bear with me as I kind of
No
stumble through
problem.
it. So what I'm hearing from you, from your presentation here, is that you're looking to stakeholders for, I guess, if we value reconsidering that distribution of cost. I'm not seeing anything on, there's anything that the company is going to be putting forward on how to value this.
Yeah, so I know we have provided different ways to calculate it in the past. And I haven't been a part of the entire process, so this is just me sharing the information that I know. I don't know exactly where the disagreement was between the distribution costs. It's just a part of the calculation that has been discussed in the past that I wanted to keep in there, just as a point that there is interest in having it. We just haven't come to a conclusion on how to incorporate it yet. So just keeping that option open. And we don't plan on using a value for it unless there's a strong interest for including something. I don't know if that
Okay.
answers the question.
No, it does. No, I appreciate your feedback. It was just I was reading ahead in the slides and got a different idea. So I'm pivoting
Okay.
over here and that's okay.
Okay.
Yeah, I guess I'll just toss in my feedback for that. Without some sort of starting point for that discussion, kind of coming from the company, I think staff would probably be okay with how it is for now.
Okay. Yeah, and definitely if you feel I'll try to go back and look. I'm not the expert on the distribution cost piece and what we have recommended in the past. So I'm not sure I'm able to speak to that today, but we'll try to get some more information on that so we can keep that dialogue open.
Sure. Yeah, I'd appreciate that open dialogue, especially if it is something that there is interest from other parties. I think the timing of getting input on that, reviewing it, having conversations, and then making sure it can be incorporated into the IRP in time will be something to keep tabs on.
Yeah. Yep. All right. Sounds good. Thank you. Okay. Are there any other questions? Okay. If not, I think what we'll do is let's take a quick 5-minute break and come back at 10:05 and we'll jump into the energy efficiency presentation. All right. It is 10:05, so we'll go ahead and get going on the energy efficiency presentation as long as Kathy is back.
I'm back.
Perfect.
All right, I'm going to try and take control of the slide deck here. There we go. Okay. Okay, so we'll start talking about the demand side management to begin with. DSM refers to reducing natural gas consumption through improved energy efficiency. So it can be a key strategy for managing demand and supporting sustainability goals. Let's see. There we go. A little bit of a delay on the slide, so bear with me here. Okay, so this is the current offering for the residential program. We have filed for changes to the residential program, and those changes are pending with the commission right now. But for the most current and up-to-date rebate information, you can always check out our website. And that's our appliance rebate offering. We also have a new construction offering. That is a 2-tier new construction offering for whole home tier 1 and tier 2. These 2 rebates include a number of energy performance targets in order to be eligible for the rebate. In addition to the whole home rebate, builders are able to stack on additional rebates, so kind of customizing their rebates by adding on water heating and smart thermostat rebates. So just in addition to their energy efficient new construction build. And then this is our current commercial energy offering as well. Again, you can find all this information on our website. Okay, what is a conservation potential assessment, or CPA? Energy efficiency is guilty of using a lot of acronyms and abbreviations, so if I'm throwing something out there and not defining it, certainly call me on that. I'll try and clarify. I try to do that as I go along through the presentation here, but let me know if I'm getting too deep into alphabet soup. So the first thing here, what is the conservation potential assessment? This is a study estimating the achievable energy savings through energy efficiency measures. This particular study includes both residential and commercial sector, and it identifies 3 types of potential, which is technical, economic, and achievable potential. Okay, why do we do the CPA? This is used for strategic planning and regulatory compliance, supports the integrated resource planning process, and it helps inform Intermountain's energy efficiency goals, portfolio planning, budget setting, and identifying new energy saving opportunities. Okay, who cares about the CPA? The resource planning team. Energy efficiency is the reduction of natural gas consumption due to increases in efficiency and are considered a resource. And of course, energy efficiency cares about the conservation potential assessment as it identifies cost-effective energy savings potential. Okay, so who does the CPA? We worked again with Guidehouse on the CPA for the 2025 update. For those of you that remember that were with the IGRAC and the 2023 cycle, Guidehouse completed a comprehensive study at that time. So we work with them again on the 2025 study. Okay, we'll jump into the update here. Okay, as I just mentioned, Guidehouse conducted the study for the 2023 IRP. The Intermountain Gas program didn't have any major program changes from the last study to this one. So rather than doing a whole new study, we asked Guidehouse to update all the model inputs for the 25 study rather than run another full-scale study. So that's what we'll go through here is what was updated for this study for 2025. Okay, on the screen here are the model inputs that were updated, which include the building stock and sales forecasts, retail rates, avoided costs, inflation rates, and discount rates. The measure inputs were also updated using the IGC technical reference manual. And other updates included extending the forecast period by 2 years and shifting the starting year for adoption of behavioral measures by 2 years. So the adoption trajectory now starts in 2025 instead of 2023. Okay, so the first one, the building stock and sales were updated, sales forecasts were updated. Compared to the 2023 CPA, the forecasted building stock is generally slightly higher for commercial and modestly lower for residential. Sorry, let me go back there. Apologies, I've clicked too many times here on the... There we go. Okay, retail rates. Compared to the 2023 CPA, rates are lower for 2024 through 25, but higher in 2026 and beyond. Avoided costs, as Brian just went through, compared to the 2023 CPA, avoided costs are lower in 25, but higher in 2026 and beyond. Yeah, Jason.
Yeah, sorry to interrupt you. So from the slides Brian showed, the updated avoided costs are lower in 2026 and onward. Could you reconcile those?
The avoided costs that Brian showed were given to Guidehouse. So I can go back and check here. Maybe I've got the wrong year, lower in 2025, but I will go back and look and make sure that we've got all the correct inputs.
Okay. Yeah, I think that especially with the drop past 2026, that near-term drop that Brian was saying, I think that might be important to verify.
Okay. We also updated the inflation rate and discount rates. Inflation rate now is 3.99%, previously was 3.15. Discount rate now is 2.68 and previously 3.51. Let's see here. We updated the measure inputs, savings, costs, and lifetimes. These were updated for 127 out of the 120 measures that are in the CPA. So a little bit of alphabet soup here. The savings estimates that were used in the 2025 study were updated with the IGC Technical Reference Manual, or TRM. And this TRM was prepared for IGC by a third-party evaluator. So the underlying resource for the unit energy savings estimates in the TRM are based on the RTF. And for measures that are not included in the RTF, the Illinois TRM was used. So you'll see the impact of these updates when we get to the final study results. The key change here is that the savings for the 95 and 97 furnaces were reduced about 75% per the IGC TRM compared to what was used in the last CPA cycle. Jason, did you have a question? I saw a hand up there for a second.
Yeah, I had a few. The first one, I just wanted to back up a little bit. Could you help me understand discount rate and some of the things that go into why that's changing?
Brian, do you want to go over that. These inputs come from the resource planning team.
Yeah, I think I want to say the discount rate comes from the regulatory group. I don't know if I think our regulatory group dropped off. I think part of it is tied to the um, cost of capital, and so I think that may be an adjustment. I'll have to go back and dig through that. I think it's part of the PGA and rate case information that regulatory does. So I'll have to do some digging on that.
Okay. Yeah, I think that's a good change for me to follow. Thank you. I did have more questions before I forget. So Kathy, I think you alluded to this at the start, but I just wanted to make sure. When you say that this is based off the TRM, and for the understanding of other people in the call, that TRM was updated part way through the ongoing filing. When you say this is based on the TRM, is that based off of the initially filed TRM or the updated TRM?
No, thanks for the question. This includes the update that the RTF did for their furnace workbook. So this is the most current version of the TRM that includes the update that was done in February.
Thank you. So that also reflects the so that wouldn't reflect the proposed program retirements and so on in that case?
No, this is just so this looks at all the measures. So did we include the ones that we're planning to retire? Is that your question?
Yeah, did it reflect those assumptions? So what you're feeding into the IRP, if the proposal is to retire, then would show retired.
No, since those changes are still pending, that was not included in the update for Guidehouse.
Okay, thank you. I think I'm out of questions for now. Appreciate it.
Mm-hmm. Okay. Guidehouse extended the forecast period by 2 years, so out to instead of 2046 out to 2046 instead of 2044, and then shifted the starting year for the adoption of behavioral measures by 2 years as well. Okay. Different types of potential. As I mentioned earlier, the study looks at technical potential, economic potential, and achievable potential. Yeah, Jason.
Sorry to interrupt again. I'm finding more questions. So those two updates, the shift from 2024 to 2040 or 2044 to 2046, and behavioral measures beginning in 25 and 2030, is that just a result of the forecast window being shifted 2 years forward? Or is there
Yes.
another Okay, so it's just the timeline.
Yeah, they're
Okay.
just trying to look at the new updated time frame.
Okay, thank you.
Uh-huh. Okay, so when it comes to types of potential, the technical potential is all feasible savings. Economic potential now adds a filter on to look at just cost-effective savings. And then finally, the achievable potential is things that are expected to be adopted by the EE programs, taking into consideration some market information about what's readily available, what's on trucks, what do customers install, what is their knowledge about those kind of measures. So that really looks at the more conservative achievable potential. In graph form, here is how the technical potential, economic, and achievable potential is forecasted through the study time period. And then as we look at going forward in the study, we're going to focus mostly just on achievable potential. So that's what we'll be talking about here as we look at running more of the scenarios against the achievable potential. Okay. So Guidehouse ran 4 scenarios on the achievable potential. They looked at business as usual, which is the first scenario, no intentionally designed change. So this is just business as usual if things were to stay about the same budget levels, same activity levels, same adoption rates, everything kind of stays same. We're looking at business as usual. The second scenario was the unconstrained historical budget, which unconstrained seems a little misleading there, but it just means that we increase program activity by increasing the historic budgets. So by adding a little bit more on the budget, how does that change what the potential measurement is? And then medium adoption is another scenario where we increase customer awareness and willingness to adopt. And then finally, the last one is high incentive, high adoption. And that reflects different assumptions about incentives and customer adoption, meaning that instead of incentives being 50% of the measure incremental costs, it's bumped up to 65%. And that we use the model to forecast some increased customer awareness and willingness to adopt. And by combining high incentive and high adoption, gets us to that 4th scenario. Okay, so this is for residential only. If we look at here, we have, again, the technical potential, the economic potential, and then at the bottom here, you can see the 4 scenarios of business as usual, unconstrained historic budget, medium adoption, and high adoption. The business as usual is the most conservative kind of forecast here, where everything is kept the same going forward as has been experienced historically. This is for the commercial sector. Same scenarios again, you have technical, economic, and then the 4 scenarios of business as usual, unconstrained budgets, medium adoption, and high incentive. And this screen here shows the achievable potential for all scenarios. So this is residential and commercial combined for the 4 different scenarios. Okay, so here Guidehouse ran a comparison of the achievable potential from the 2023 study versus the 2025 study, with some of the reductions in the savings estimates for the measures there from the TRM. You can see that the potential is reduced, along with some other factors that impact this reduction, as I'll go through those here. The combined effect of the global updates was, in general, to increase the benefit cost ratios using the UCT compared to the 2023 study. And this is driven primarily by higher avoided costs in later years and combined with a lower discount rate, which makes the future years more important. For the business as usual scenario, you can see the achievable potential results are lower overall than the 2023 CPA, and that the difference grows over time. So this chart shows the residential and commercial separately, but also shows the combined potential there at the top row. The measure competition group, when we're talking about measure competition group, we might have a number of measures that do the same thing, but they have different efficiencies. The best example is for the space heating measures, where you may have a 95 furnace, a 97 furnace, and a gas heat pump. So in this measure competition group with the highest potential, it's residential furnaces. And these together account for 1.2 million therms of the achievable potential in 2024. This was 1.4 million in 2023. So we're seeing that reduction due to the change in the unit savings estimates. And that was about a 75% reduction in the savings estimate based on the IGC TRM. So the other thing that we're seeing in that space heating arena is the inclusion of the gas heat pump, which becomes more cost effective in these years, but the increase in the gas heat pump savings is not quite enough to offset the reduction that we see in the furnace measures. Yeah, Jason.
So the natural gas heat pump, that is not an existing measure currently, is that right?
It's not a measure that we rebate currently, no, but it is
Great.
a measure that is included in the TRM and in the study.
Okay. What year does the study assume that those are going to come online? Because if I recall, that's a fairly new technology.
It is a new technology. I'd have to look in the study. I may have to ask Guidehouse about that, because I think the residential gas heat pumps are commercially available now. I don't know that they're readily available in our region, so I'll look into the study and see where they have those coming online and what year they become cost effective.
Okay. Yeah, I'd appreciate that
Sure.
that information as a follow-up. Thank you.
Yeah. Okay. In the other scenario, this was the second scenario of the unconstrained budgets. The long-term potential is higher overall versus the 2023 CPA. And this is really driven by an increase in the commercial sector potential as more measure instances are being modeled as cost effective. So again, you can see the combined results on the top row there, and then the residential and commercial separated out in the next two lines there, two sections of the chart. Achievable potential by sector as a percent of total sales. It's part of the big picture results. As big picture, it's still pretty small. If we look at the most current or the most near-term years, we're still looking at a little over 1.5% of potential as a percent of potential sales. So the energy efficiency contribution is still pretty small overall in the big picture for the IRP plan. What's next? The IRP team will apply the study results for resource planning. And as I mentioned, the Energy Efficiency Department, we have filed for residential changes to the residential offering, and that's still an open case that's under consideration by Commission. And we'd also like to propose changes to the commercial program offering soon. Yeah, Jason.
All right, thanks. For that last point, is there a timeline with visibility to when those commercial programs might be proposed? And if it lines up well enough, is there some merit to including those proposed changes just as, I guess, potentially a scenario to see what would happen?
Timing wise, I think we have been busy with the residential offering and waiting on the resolution to that case. But I think next steps, we'd like to propose changes most likely to the stakeholder committee before filing. And I guess clarification on your question about the scenario, what you're asking there.
Yeah, so to add a little bit, if I'm assuming here from the company's perspective, if the proposals that you are thinking of making, if those are relatively set, relatively firm, um, is there sense in including them in this IRP potentially as a scenario? So we'd have our base case scenario, as is, and then just as proposed, include all those changes just to get a sense of what might be changing in the future. I mean, the IRP forecast is well past 2026. I imagine it'll start capturing some of those proposed changes.
Yeah. I guess I would have to say more study required. The CPA really is designed to capture potential of what could be. We haven't ever gone back and updated the CPA plan with the actual energy efficiency program because it is designed just to identify potential. I guess if you're wanting to look at the actual program design and potential savings from that, I think that would be something different. Not that it couldn't be done, but that it probably wouldn't be applied to the CPA or IRP inputs.
I agree, Kathy. I think getting into the weeds of those proposals is probably held best done in a different location. But your statement that the CPA is designed to capture future potential is exactly to my point of, at some point down the road within the scope of the CP or of the IRP forecast, you have proposed commercial or planned commercial changes should the forecast include those. And if more study is required, that's fine, but that's what I'm trying to get to.
Yeah, I guess I'll have to follow up. I have to think through that. Because anything that would be used to design the commercial offering would come from the CPA. The CPA is used to inform cost-effective savings potential. So it's almost like going backwards by designing the program and then going back and applying it to the CPA. And we haven't done that. That hasn't been part of the process or the intention of the CPA.
Mm-hmm.
So I'll have to think
I
through
hear
that.
your point there. That doesn't make a lot of sense. I still feel like there's some consideration that should be given to within the IRP's load forecast, because the CPA feeds into that, and maybe there's an opportunity to interject some potential design based on the results of the CPA. What might that look like on load forecast? Maybe it's a different scenario then.
Yeah, I'll jump in. Jason, so what we do is we take the energy efficiency projected savings from Kathy and we apply it to the future load. And so it goes into our Plexos model, which we'll discuss at IGRAC 3. And it goes in as a decrement to demand in the future. And we model these different scenarios. And so we'll have different outputs for each of these different scenarios of how it impacts demand and how it would impact upstream resources.
Oh, so what I'm
yeah.
getting is that the load forecast already will include those proposed commercial changes?
Yes.
Oh, okay. Great. Then my point is taken. It'll already be in the forecast, and I think that's appropriate.
Yes. Yeah, sorry, I wasn't fully understanding the question, but then I finally got to it there towards the end. So yeah, it should be included in this IRP modeling.
Okay.
But I just want to clarify real quickly that Jason's question is, when you do that, Brian, and you apply the EE inputs into the model, you're taking information that's based on the CPA, on the conservation potential assessment. Jason's question is, should we instead be using what the actual program offering is rather than what is informed by the CPA? Am I getting that, Jason?
I guess if they're different, I would kind of anticipate that those proposed program changes are based on the CPA. So the savings are there, but if there's any differences, because I know there can be some shift between what a CPA says is out there and what the programs are anticipating to capture.
Correct. They will be different because the CPA is looking at potential. So it is including a host of a number of measures. Now, can the program cost effectively offer incentives on all of those measures? Unlikely. Because once we look at the cost effectiveness of administering all of those measures, are they still all cost effective? That's not likely, given budgets and that sort of thing, resources that are needed to administer that type of plan. So if I'm understanding right, Brian, you would look at basically what comes, the CPA outputs that are provided here and reviewed here, not what the actual energy efficiency offering is now or in the future.
Yeah, Kathy, I think that was a great summary that got where I was going. But
Gotcha.
yeah,
Okay.
that can only work if, you know, the program changes that you have in mind are developed enough to actually bring in here at this level.
Yeah, I mean, if we were to offer every single thing that's identified in the CPA, yes, they would be the same. But they won't be, because we just, as a program, given our budget and resource limitations, would not be able to do that. But the CPA is used to inform where cost-effective savings are and how do we implement that. So
yeah, so Kathy, to reframe my question, I'm with you on that part. The question is, the planned programs, are those developed enough at this point in time for it to be reasonable to include them? Or are they still needing time to develop before they can reasonably be forecasted out?
that they can be forecasted out to put into the IRP?
Yeah.
That just isn't something that we've ever done or applied to IRP planning.
Okay.
Is this a new, this would be something new that staff would want to see us do in order to
I don't think we're that far yet.
Okay.
Is it even a possibility at this point?
Ooh, yeah. So I don't know. I guess that's the ultimate bottom line. Because Guidehouse operates the model, we would have to go back to them and ask them to make the input adjustments to get get the study outputs for IRP.
Okay, so something
those
to be done
changes.
then. All right. I think that answers the question of there would need to be more work. Thank you.
Yes. Gotcha.
Okay,
Sorry, that was
we
very
made it
long-winded,
there.
but I think we got there.
Yeah, we did. Okay. I'm so
Perfect.
sorry. I have more questions.
No, that's okay. I appreciate it.
Appreciate everybody's patience.
Yeah.
So in the 2023 IRP, staff had commented that the historical data used to calculate that CPA, which is being updated in this IRP, may have been overstated and resulted in overstated forecasting of energy savings potential. How has that been corrected in this IRP update?
I think one of the major ways you're going to see that is that we use the TRM for savings estimates, which we didn't have a TRM before. And so implementing the TRM into the CPA use for the unit energy savings, you saw that reduction in the furnaces by almost 75% compared to what was in the 2023 study. It's probably the biggest change that you'll see in how we're trying to, I guess, tighten that up and use the best information that we can for forecasting potential.
Okay, so you have some inputted updates, but if I'm remembering those comments correctly, they were it's a model. It needs to be calibrated, and it was calibrated using historic data that had, assumed those overstated, or at least by staff's comments, overstated results. So has there been any adjustment to the calibration process?
No, it has not been recalibrated from the way it was calibrated in the 2023 study.
Right, thank you. All right, I think I'm all out of questions. I just had a little bit of feedback though. This is difficult because Kathy, as you said, this is an ongoing case, and
Yeah.
nobody can speak for the commission and what they say. But I think that for this IRP, it's going to be important to have some additional granularity, kind of indicated by the direction of that filing. What I have in mind is, a scenario either in the CPA or and probably trickling into the IRP for the proposals in that current case. So there's going to be, I believe, the proposals for some DSM measures being retired. I think that should be reflected in the IRP. And as Brian said, I think the time to get those in there is now. And I think we should also have a scenario to reflect staff comments. It's going to be imprecise. It's going to be just kind of some cases, and truly will be defined by what the commission orders. But I think we can at least set some boundary conditions and assume the commission is going to fall somewhere in the middle. And I emphasize that just because there's large differences between those two positions.
Between the two positions, which two positions?
Between the proposals and staff comments.
Okay. I think that, yeah, we can definitely look at that. I appreciate the feedback. There are lots of measures that are included in the CPA that we don't implement from a cost effectiveness standpoint that we, can't implement, or, maybe it's something that customers wouldn't adopt, or the technology like gas heat pumps, they're just not readily available in our region. But we don't take those out of the CPA before it's used as an IRP input. So by the same token, you're suggesting that we would take out the measures that are being retired, even though we don't kind of cull the measures list by things that don't get implemented.
Yeah, I can't speak too specific to what that looks like at this point, Kathy. All I'm saying is that there's movements in the direction in that filing that I think need to be reflected in this IRP somehow. I don't know how that looks. It's just there, a lot of ways that filing could turn out. And, in order to have good program planning for DSM in the future based off of this IRP, we need to have, a CPA that reflects things that are, actually or going to potentially exist depending on that commission order.
Okay.
And, how that looks like and what that needs to go into the CPA. I'm happy to work with you and figure out what it is. But I think that those are situations that we should have visibility to in order to inform that planning in the future.
Okay, sounds good. So Brian, I guess we'll leave it as more study required as to what actually goes into the IRP inputs from the CPA.
Yeah, I agree.
Okay, got it. Thanks, Jason. I appreciate that. Any other questions for energy efficiency? We still have Brian's feedback loop. If you do think of something in the future here, I'm happy to answer more questions. Thanks, everyone.
All right, thanks, Kathy. We already took a break, so I think what we'll do is we'll just jump into the next presentation. If Eric, if you're ready.
Yep, I'm here.
Hopefully I'm ready.
Okay.
I'll try to take control here.
Okay.
If I can get this to work. Okay. Looks like I'm set there, am I?
Yeah, I think you're good to go.
Okay. So I'll just go over gas supply. Once again, my name is Eric Wood. I'm manager of gas supply at Intermountain. And so we'll just go over kind of general gas supply concepts in terms of how we get gas to our system and how that gas flows into our distribution system. So when we're talking about gas supply planning, the goal is, really reliability 365 days a year. And that takes a lot of planning and process along the way. Security is one thing, delivery on the coldest day. We have some really big peak days. Our peak day, can be in the high 380,000 decatherm range, and low can be in that 30,000 range. So a lot of variability there in order to meet that coldest day. Obviously, we want competitive and stable prices, and through a mix of fixed price hedges and efficiency to meet our future growth, as Kathy just discussed. And then we frequently evaluate the portfolio all the time. So it's a year-to-year process, month-to-month, weekly, and day-to-day process in order to evaluate that portfolio. Let's see. So natural gas supplies, where does our traditional supply come from? The natural gas supply, the molecule is the actual commodity, and we use interstate pipeline capacity to transport that to our system. And then we also have storage facilities throughout the Northwest that we use to also pull that storage molecule out and transport it to our system. And then energy efficiency is also a part of that. Non-traditional supply would be renewable natural gas. Intermountain does have several renewables on our system, and that those are usually dairies for now, and we have a landfill as well. And so those are kind of untraditional supplies. And then hydrogen, if we were to actually make that work in the future. And so that's something that we would look at as well. So where does our natural gas come from? So the vast majority at Intermountain comes from Canada, and mostly British Columbia and Alberta, and that's about 90%. And then we do get some from the Rockies supply in Wyoming, Colorado, and Utah. And so access is just dependent upon available transport capacity, and most of Intermountain's transport capacity is from Canada South. And so that's the reason that most of our supply comes from Canada. So this is just a look at North American gas plays in North America. Just kind of shows you a general idea of where some of these gas plays are. Obviously, there's a big play in Canada. It's called the Western Canadian Sedimentary Basin, and that's where most of Intermountain's gas is transported from. So our gas supply forecast observations. So there was a really robust increase in shale gas production. That was about 2008 time frame until currently, and I can kind of show you a graph later that kind of shows you that. And then mature basins like the Western Canadian Sedimentary Basin that I just talked about, and then the Gulf on and offshore, even though we don't actually source gas from there. But today there's still ample supply and versus demand. And I think just the other day, the U.S. set a new high record of 108.1 BCF a day or something like that in gas production. So still ample supply. And then this is kind of monthly U.S. Dry shale natural gas production by formation. Just gives you a little bit of kind of a sampling of what the formations are and kind of those production levels. This is natural gas by consumption by sector. As you can see, the residential is kind of that blue line. It's fairly flat, and this is countrywide too, so a little bit different here in Idaho. Obviously, we've experienced some growth, especially in the Boise area. And then you can see kind of the power production there has really taken off with kind of retirements of some coal plants, and some of those coal plants actually being converted to natural gas. So electric generation is huge. The natural gas system is huge for electric generation currently. So that's definitely changed a lot in the last 10 years. So gas supply pricing. So it's obviously a commodity, and we trade it on the open market. And most of the markets are pretty liquid. There's market points where we trade. And some of those rather market points are much more liquid than others. And so it just varies on the market point where we get that. And then the price follows supply and demand fundamentals, storage, transport resources, and supply. And so all those, and then of course, weather is, a factor where, plays a big impact on price. And then I'll show you a little bit of price history and forecast. This is just kind of a sampling of data that I had from back to 2006 of the indexes we use, both Sumas, Rockies, and ACO, and just kind of some examples of what can occur. And you see kind of this big spike here back when Enbridge happened back in 2018. There was a big spike there. And then a couple winters ago where we had this big, huge issue where there were some constraints going into California. And so a lot of gas flowing south was having to be rerouted into California. And then we had really low storage levels going into the winter, and then really kind of pretty unprecedented cold that kind of continued on over the winter. And so with those low storage levels and kind of that constraint, we had some really high spikes in the front of the month index, both at Rockies and at Sumas. See if this will pull up. I don't know if that last one pulled up, did it? Oh, there it goes. Sorry about that. So this is kind of Brian's team. What they do is they put the forecast together, and that helps gas supply also kind of evaluate our portfolio, what we're going to need for future needs. And we take a look at that, and then day to day we adjust accordingly. Intermountain's long-term price forecast is based on a blend of the current market pricing along with the long-term fundamentals. The forecast includes sources like Wood Mackenzie, EIA, Northwest Power Conservation Council. So we look at a lot of different kind of price forecasts, and then we use weighted prices for those sources based on historical performance. And so Brian's team is evaluating those. And then, it's not a market guarantee where the market will ultimately finish, but Henry Hub NYMEX is 100% of the forecast for the first year of its most current information, and that provides some direction as a future markets price. Intermountain's gathering renewable gas information and plans to model RNG as a potential resource for upstream optimization process as well. And this is just a look at what that forecast looks like. And then you can kind of see the weights over on the side. We use ACO at 80%, just given that that's primarily where most of our supply does come from. So we'll talk a little bit about transportation and storage. So Intermountain holds firm transport on 4 pipelines. So there's 2 upstream and then 2 in the US. So that would be Nova, Foothills, and then GTN, and then ultimately in delivery on Northwest. So interstate transport capacity, it's delivering to Intermountain service territory. And so we have firm capacity held directly by Intermountain. And then we do have some city gate supplies that are delivered on our behalf directly to our system from a third-party marketer. We do use capacity segmentation, which on Northwest Pipe has a really flexible system. And we have segmented some of that capacity in order to utilize more valuable segments more appropriately. And then while we can actually release some of that segmentation to other parties that can utilize it. And for our benefit in terms of we're mitigating some of that cost. And then market forces always drive new capacity projects. And so we're always looking at the forwards with the IRP team in order to determine, do we need more capacity and what's that capacity going to look like for our needs in the future. And the capacity release mitigation is part of Intermountain's process too, just to kind of go back to that briefly. But we do release capacity when we're not using it, so we can actually in turn make money back on that capacity as a capacity release mitigation. And then this is just a quick look at all the upstream stuff. Northwest is all the red pipeline there, of course, and it flows all the way across southern Idaho. That's the main portion that we utilize. And then if you can see the gray dotted line that comes down, this is GTN that comes down across northern Idaho into Washington and into Oregon, ultimately intersects with Northwest Pipe, and that's how we get delivery of the upstream gas that's here at ACO. This is just a quick chart of our current capacity resources of the different locations. Like I mentioned, we do have that one city gate deal in there. We have some Rockies capacity. The Stanfield capacity represents the interconnect with GTN for the northern upstream pipelines. And so that Stanfield capacity is Stanfield South into Idaho. And then our storage resources are bundled in there too. So just kind of shows you the mix of our resources in order to meet that full peak day demand. So storage, what is storage? So two different things. Storage can be underground, which is a natural man-made structure where natural gas can be injected and stored for later retrieval. It's normally injected during periods of lower demand and lower prices. And then gas is usually withdrawn during periods of higher demand and higher prices during the winter, of course. And so we do use it to mitigate price. And so not only do we mitigate price, but we also do it to mitigate kind of our ups and downs in our system. So demand curve is not linear, rather, sorry. And so, demand curve goes way up in the winter. We have to pull storage out in order to meet that demand curve. Annual supply curve is somewhat linear in that our transport is linear. We have the same amount of transport month over month, year over year. So it's not feasible to meet peak demand with only interstate capacity, and then we have to use our must-take purchases and must-take purchases alone. And so storage enhances kind of the winter peak deliverability. Without storage, we wouldn't be able to meet those needs on a day-to-day basis. We do use storage for daily balancing it too, as well. So we do buy and sell on the market in the day, but we also maximize our storage in and out as well in order to balance our system. This is just an example of low duration curve, just kind of shows you kind of what that looks like. You can see transportation capacity is flat. In the winter, we use storage withdrawals in order to meet the capacity. And then in the summer, it's just the opposite, where we're injecting into storage during times of low demand. Some of these slides are a little touchy. They kind of take a little while to load. So like I talked about, storage use sources are used for needle peaking. When we have those really high days, we can turn to those storage resources in order to meet our demand. So we're not always having to turn 100% to day gas market. We use it also for winter base load. So we do have a kind of a winter base load curve that we somewhat rely on day to day. We use it for price hedging as well too. So if prices are really high, we'll draw more out of storage if possible. And then system integrity and emergency issues, where we've had problems upstream, where we've had to possibly withdraw more out of storage because of transport issues. So two types of storage: LNG, liquefied natural gas, and then underground. And we do have both facilities. LNG, it's liquefied natural gas stored at minus 260 degrees Fahrenheit. It liquefies, and so it's stored in a tank. It's pure methane. It's non-corrosive, non-toxic. So there's a high regasification rate when you withdraw that. It withdraws pretty quickly, but the injection process is much slower. So it is ideal for needle peaking and system balancing. And we do use Plymouth quite a bit in the winter when we have those big high peak days, because we can draw quite a bit of capacity out of that storage facility. And like I mentioned, liquefaction is slow, and so it kind of limits the cycling time. It's also pretty energy intensive, and it's somewhat expensive. So we don't try to use Plymouth as much as possible, but we do need it in those times of really high demand. It's stored in above ground tanks. They're big, giant tanks. And then the boil off is always caught and then recaptured. So the natural cycle of the liquid will boil off at ambient temperatures, and then the facility just regenerates that and then reliquefies that or puts it back into the system. This is just a quick picture of the Plymouth LNG, and I think it's just taken from one tank to the other. Someone standing on one tank looking across to the other. There's two tanks there. And then underground, of course, gas is injected under high pressure into these depleted wells and salt domes and aquifers. So it's just underground well storage. Maximum daily withdrawal is typically less than liquid storage, but it offers a little more flexibility in and out. Injections are faster, and cycling costs are lower too than the liquid storage. So a little bit different type of storage, and it's used kind of more of the day-to-day operations and sometimes day-to-day balancing if we need it. So these are the locations and the types of storage. So we do have one system that we own. It is owned by us. It is behind our gate, the Nampa gate, and it's located here in Nampa. And so that's one facility that we have. The rest are leased. And so Plymouth is leased storage, and that's owned and operated by Northwest Pipeline. I'm sorry, the Rexburg is also owned by us. Rexburg is a small satellite facility that what we do is we take gas out of the Nampa LNG and we transport it to the Rexburg facility. It's used mostly for operations at the end of the line at Rexburg when they kind of get low pressure during really cold events up there. So we can liquefy or vaporize out of that facility to support the system at the tail end of that lateral. Jackson Prairie and Clay Basin are both underground storage. One's on Northwest and one's on Questar. Now Mountain West. I forgot to change that. But those facilities are used kind of for our base load storage curve during the winter, and then day-to-day operations during the winter as well. And then those locations, clay basins, down here, kind of on the border of Oregon and Wyoming, or I'm sorry, Utah and Wyoming, get my geography right. And then of course, Nampa is here in Nampa, and then Rexburg is over here at the tail end of the lateral. Plymouth is in this South Central Washington location here in Eastern Washington. And then Jackson Prairie is over in Western Washington as well. And so we transport from all those facilities. And then this is just a look at the storage facilities that we currently have and demand. And so you can see we have quite a bit of capacity in there, about 11.5 of capacity, and then maximum withdrawal of 315, 626. And then so we can withdraw quite a bit out of there. And that really helps us with price mitigation kind of during those peak events and to make sure that we're covering our load. Just another sample. This is kind of a supply stack of what we would do in most cases. And so just kind of another sampling of the previous kind of slide. Just shows you the injections, year-round gas that we have. We add on to that storage resources. We add on to that our city gate transport, and then we add on kind of our needle peaking resources like Plymouth in order to meet that peak demand. And any questions that you may have? All righty. I'll pass it back to you, Brian.
Perfect. Thank you, Eric.
Yep, you bet.
Yeah, I'm not seeing any questions. Let's move on to these next two slides, and then I'll open it up for questions at the very end. So again, here's a reminder of how to provide feedback. Just reach out to us at irp.comments@intgas.com. And please provide comments as soon as possible. That way we can incorporate it into the IRP. And then the next meeting, so the third IGRAC meeting, will be September 17th. That is the corrected date. When we sent this out, it said September 13th, I think. We will not be presenting on a Saturday. So it will be September 17th, and same time. We'll discuss the potential capacity enhancements, as Kathleen had mentioned. We'll discuss resource optimization, planning results, and then the remaining IRP process. So this will be our last IGRAC meeting. And then we'll put together a draft of the IRP and provide it to everyone, all the stakeholders. And then there will be some time for a little bit of time for review and feedback, and then we'll put together the final IRP to be filed. I believe that'll be sometime in December. So I'll open it up for last questions. If there's no other questions, we'll let everyone go. So I'll just pause for about 7 seconds.
Looks like there was one in the chat, Brian.
I posted one on the chat just about running out of gas. Has it happened?
So it does, but it's not typically system-wide. So, it's happened on different systems. So, Cascade has had an issue where we had a lateral that ran out of gas. And so we had, no service to those customers. Happens in North Dakota on our sister utility out there where they have freeze-offs. It's happened, to a small portions of Intermountain. It's usually like distribution system kinds of issues. We have had, low pressure on the upstream pipeline at times, and the utilities in the Northwest kind of get together and determine an emergency action plan in terms of what we're going to do in order to boost that. So yes, it does happen, but it's usually to, small segments of the system. So Intermountain's been pretty fortunate. I don't know of any that I can recall other than like local small disruptions from line cuts or line breaks.
Great, thanks.
Yep.
Yeah, Kathleen's on. So a couple years back, we lost some customers in, I believe it was that around the Boise area. But it's rare. The goal is not to lose customers, of course. But yeah, it can happen, or growth can be like occurring at high levels. I think that's what happened with Boise. So we needed like a reinforcement or something. But yeah.
Great, thank you. Thanks for the question, Matthew. Are there any other final questions before we wrap up? Okay, I'm not seeing any other questions. I'm not seeing any hands or anyone coming off mute. So thanks to everyone for joining today and all the engagement during today's presentation. Appreciate it. And we'll see everyone at the third IGRAC meeting.
Thanks.
Thank you. Bye.